Have we found alien life? Since the James Webb Space Telescope began its operations, there have been two questions that the media and the public have always wanted to explore: the truth about the primordial universe, whether the hypotheses we have struggled with and developed over many decades, including the Big Bang, are entirely accurate or not, and whether extraterrestrial beings exist, and if so, where in space they might be. With James Webb, these questions are being illuminated more than ever, particularly the mission to search for life beyond Earth. After many attempts to send signals in various ways beyond Earth, only to receive silence in return, today the quest for faint sparks in the universe has been simplified and fundamentally transformed into a search for signs of life. However, this task remains immensely challenging and demands observations with vast amounts of data. No one knows if extraterrestrial beings exist, but in this vast universe, we truly hope that our species is not alone. The harsh environment of space is a reality, and humans must always prepare for interplanetary accidents. Thus, the search for a second habitable planet is the longest-term contingency plan. This is also one of the most critical missions of SETI. SETI, different thoughts. The modern story of SETI began in 1959 when scientists Giuseppe Cocconi and Philip Morrison of Cornell University published a paper in Nature titled "Searching for Interstellar Communications." The article started with a simple assumption: if intelligent beings knew we were here, they might attempt to communicate. This premise still forms one of the cornerstones of the field. Today, it has become part of public research and the quest for extraterrestrial civilizations. When asked whether he truly believes in extraterrestrial life, Seth Shostak, director of SETI Research, joked, "Of course I believe. I mean, am I doing this just because I like the fancy office? Doesn't it look like it?" This is an affirmatively toned jest. Many of us believe that extraterrestrial life is plausible. With the vast amount of matter in the universe, the existence of life on other planets is not implausible. However, the vast distances between planets and galaxies and the low probability of life have hindered humanity's ability to uncover the truth. Humans once thought the entire universe was encapsulated within the Milky Way, and we could only observe 8 planets in our solar system. Over time, our knowledge of extraterrestrial life has evolved. Today, we have a certain understanding of the skies. We understand how the universe formed, and we know that most stars have planets orbiting them. Over the past century, the question of extraterrestrial life has incessantly fueled human curiosity. This has spurred various efforts to search for signs of life in the universe, from collecting soil samples from Mars with the Perseverance rover to observing the atmospheres of distant exoplanets through space telescopes. A part of this endeavor is the search for extraterrestrial intelligence, known as SETI. SETI projects primarily focus on detecting non-natural or abnormal signals that may emanate from different regions of space, potentially indicative of technologically advanced life forms. Some projects explore the transmission of signals from Earth as a means to demonstrate the existence of intelligent life here. The potential consequences of contact with an advanced alien species have prompted discussions not only based on science but also on ethics and policy. Much of the search for extraterrestrial intelligence relies on the outcomes of human intellect, as they represent the most comprehensible signs of technological advancement. While extraterrestrial civilizations may possess technologies far beyond our most primitive imaginings, there could still be commonalities. Electromagnetic communication is one such example. However, we have no reference knowledge from beyond. What type of signaling devices would extraterrestrial beings use? The electromagnetic spectrum is vast, ranging from low-frequency radio waves to high-frequency gamma rays. Fortunately, there's a practical constraint that narrows down the possibilities. Earth's atmosphere blocks much of the spectrum. Cocconi and Morrison reasoned that an advanced civilization would recognize our limitations and transmit something detectable on Earth. Thus, humanity's tentative steps began. We have shouted into space and listened to the distant murmurs of the cosmos. During the remainder of the 1960s, SETI research was almost dormant, except for some searches in the Soviet Union. Starting in 1971, the next two phases of Project Ozma, called OZPA and OZMI-EI, employed larger dishes and listened to more stars. In 1973, another CI search began, using a radio telescope called Big Ear at Ohio State University. Big Ear was a flat aluminum dish as wide as 3 football fields, with reflective panels at both ends. On the night of August 15, 1977, the Big Ear radio telescope detected a signal from the constellation Sagittarius that was 30 times stronger than the background noise of the universe, at a frequency of 1.420 megahertz, the characteristic frequency of the hydrogen line. No one paid attention to it for several days until a volunteer data analyst circled the signal in the printout from the previous week and wrote, "Wow," in the margin. However, despite decades of subsequent searches, that signal was never heard again. NASA gets involved. In the late 1970s, NASA entered the fray, providing a significant boost to the SETI field. They devised a 2-pronged SETI research plan. One part of this plan was an organized search across the entire sky, conducted by NASA's Jet Propulsion Laboratory, primarily based on the agency's Deep Space Network. Concurrently, NASA's Ames Research Center would conduct targeted searches of stars similar to our Sun, using observatories such as Arecibo, Green Bank, the Parkes Observatory in Australia, and the Nankai Observatory in France. However, even with NASA's involvement, projects searching for extraterrestrial life or intelligence still faced much controversy and criticism. In the early years, the idea was deemed as fringe and faced government prohibitions. Observational efforts and research struggled due to lack of funding. In 1979, Senator William Proxmire awarded his Golden Fleece Award of Shame to the program, branding it a waste of taxpayer money. 3 years later, Proxmire received backlash from SETI supporters for earmarking funds for the project. Carl Sagan personally met with the senator to convince him that SETI was a worthwhile endeavor, arguing that it would spur the development of advanced technologies and could provide evidence that Earthlings could survive the technological adolescence if we were to encounter other beings. A petition signed by leading scientists and Nobel laureates bolstered Sagan's argument. Proxmire eventually relented, and after another decade of development, NASA's SETI program officially went online in 1992, rebranded harmlessly as the High-Resolution Microwave Survey. Exoplanets. After years of struggle, exploration, and development, today, projects searching for extraterrestrial green seeds outside of Earth have garnered widespread attention and attracted significant government funding. With James Webb, hypotheses become clearer, and the mission to find a second Earth has become easier. Webb can observe dust clouds in the atmosphere of a strange giant gas planet and detect carbon monoxide and hot water molecules in the multicolored image of another giant gas planet. Furthermore, the Habitable Worlds Observatory, HWO, will attempt to directly image Earth-like planets in the 2050s. The impressive mission hopes to observe signs of oxygen, water vapor, carbon dioxide, and ozone. Oxygen and ozone are produced and sustain life on Earth, so they are natural biological indicators. But some astronomers are concerned that oxygen on other planets could also be produced by complex but non-biological chemical interactions. Even if oxygen is detected in the spectrum of a directly imaged planet, multiple lines of evidence, detecting multiple molecules and modeling where they come from, may be needed to rule out any false positive results. The prospect of observing signs of biology in a short time frame can be improved through the technique of transmission spectroscopy. This technique has been at the forefront of exoplanetary atmospheric science for the past 2 decades, as directly imaging exoplanets is very challenging. Astronomers have used JWST to place strong constraints on the size and composition of rocky planets transiting red dwarf stars, such as LHS 475b, GJ 486b, and more recently, TRAPPIST-OSB. However, JWST has not convincingly detected atmospheres on these rocky planets because these red dwarf stars could also have water vapor in their atmospheres and mimic planetary spectroscopic signals. To counter this, astronomers will need to learn more about these peculiar stars before they can handle the spectroscopy of their planets, even though the chances of success are very low. K2-18b, super ocean. However, signs of life may not appear on planets the size of Earth. In recent years, some astronomers have suggested that so-called mini-Neptunes, with masses several times that of Earth, could have large oceans hidden beneath their inflated atmospheres of hydrogen and helium. The major challenge is that astronomers still lack precise measurements or robust models to definitively prove what lies inside a downsized Neptune-like planet. And with all the uncertainties surrounding the origin and evolution of life on rocky planets, we know even less about how life could arise in a vast ocean with high pressure. Despite the risks, this challenge remains enticing for researchers, as the inflated atmospheres and prevalence of hydrogen and helium on mini-Neptunes make them easier to observe through spectroscopic methods compared to terrestrial planets with thin atmospheres rich in oxygen and carbon. In this mix, there is a possibility of containing water vapor, methane, carbon dioxide, and even biological gases, all of which could rise high enough to be detected through more reasonable observation programs. Based on this, they have identified some suitable candidates. At the end of August 2023, the keen eye of James Webb suddenly discovered a super ocean that could harbor the hope of life. It was none other than K2-18b, an exoplanet described as similar to the first planet the Kuiper Group visited in the movie Interstellar, located outside the solar system and orbiting close to the cold dwarf star K2-18. The planet K2-18 resides within the Goldilocks zone and is 8.6 times the size of Earth. This planet orbits its parent star every 22 days at a distance of 0.15 AU, with a companion, a planet 7.5 times the size of Earth named K2-18c, but it may be too hot to support life. The just right distance from the cooler parent star, then the Sun allows K2-18b to receive light about 1.28 times that of Earth and has an average temperature of 2 degrees Celsius. Astronomical observations have shown that this planet has excessive methane and CO2 in its atmosphere. According to NASA, the presence of these carbon-carrying molecules, along with the lack of ammonia, NH3, may indicate a hydrogen-rich atmosphere surrounding an ocean world. Previously, the Hubble Space Telescope detected evidence of water vapor in the atmosphere of the planet K2-18b. This discovery, described in a September 2019 study, has enabled scientists to continue studying K2-18b. In addition to the presence of water, the James Webb Space Telescope also detected a very special molecule called dimethyl sulfide, DMS, that may be present on the planet K2-18b. Astronomer Niku Madhusudhan, a professor of astrophysics at the University of Cambridge, emphasizes the need for further research to confirm the presence of dimethyl sulfide. For exoplanets, DMS could become more direct evidence, as on Earth, dimethyl sulfide can only be produced by life. However, this discovery is still controversial because DMS does not produce distinct spectral features in their data like carbon dioxide or methane. Although their planetary atmosphere models allow for the existence of DMS and sometimes even more DMS, the noise in their data could be due to DMS being too adaptable, as the spectra could be explained without the need for DMS. Shortly, JWST observations of the transmission spectra of small ocean worlds could serve as an intriguing testbed for hypotheses about life in the universe. Or they could become a challenge for astronomers. As JWST continues to delve deeper into more precise observations of planets around red dwarf stars, astronomers will have to deal with pollution signals from these stars before any claims about water or life can be confirmed. However, in the long run, all these transmission spectra could be blurred by direct imaging with HWO, and measuring the amount of oxygen on rocky planets orbiting sun-like stars. Evidence of life in the solar system. CD doesn't stop at distant exoplanets outside the solar system. In fact, we haven't fully explored all 8 planets and their moons. In other words, life outside of Earth may exist at very close distances. But recent discoveries of potential biological phosphine in the clouds of Venus remind us that at least some of these components also exist elsewhere in the solar system. Mars is one of the most Earth-like worlds. This planet has a day of 24.5 hours, polar ice caps that expand and contract with the seasons, and a variety of surface features formed by water throughout its history. The discovery of a subsurface water lake under the southern polar ice cap and methane in the Martian atmosphere, changing with the seasons and even throughout the day, makes Mars a very intriguing candidate for life. Methane is significant as it could be produced by biological processes. However, the true origin of methane on Mars is still unknown. Perhaps life once had a foothold, with evidence suggesting that the planet once had a much more benign environment. Today, Mars has a very thin, dry atmosphere, almost entirely composed of carbon dioxide. This exposes Mars to a lot of solar and cosmic radiation. If Mars retains a reservoir of water beneath its surface, then the possibility of life is not out of reach. To advance the investigation, NASA initially decided not to directly target the detection of life. Instead, the 2 rovers, Spirit and Opportunity, conducted detailed surveys of the Martian environment, confirming potentially habitable conditions on Mars, partially through geological evidence of past water flow. Mars orbiters, such as NASA's Mars Reconnaissance Orbiter and Mars Odyssey, also played a role in mapping the terrain and selecting landing sites. The Curiosity rover on Mars even demonstrated stronger evidence of past habitability, collecting evidence of abundant water, organic molecules, and potentially habitable environments in Mars' distant past. Today, the rover continues its work at the base of Mount Sharp, where it continues to find evidence of past water activity. NASA returned to the business of life detection with the arrival of the Perseverance rover at the Jezero crater in February 2021. Once a lake, complete with a river delta, Jezero appears to be an ideal location to search for signs of past life on Mars. Exploring Mars in depth will also serve as a platform for the upcoming broader search, surveying the icy moons in the outer solar system to look for signs of life in the vast oceans hidden beneath their surfaces. NASA has invested heavily in the search for life on Mars, and the lessons learned will be invaluable as we observe other potentially habitable places in the solar system, such as the icy moons orbiting Jupiter and Saturn, exemplified by Europa. Europa, discovered by Galileo Galilei in 1610, along with the other 3 larger moons of Jupiter, is slightly smaller than Earth's moon and orbits Jupiter at a distance of about 670,000 kilometers every 3.5 days. Europa is continuously squeezed and stretched by the competing gravitational forces of Jupiter and the other Galilean moons in a process known as tidal flexing. Liquid water tops the list of components essential for life, and Europa has plenty of it. Scientists believe Europa harbors a salty ocean beneath its icy crust, with twice the amount of water as all of Earth's oceans combined. Dissolved water carries nutrients for organisms to consume, transports vital chemicals within living cells, supports metabolic processes, and enables those cells to expel waste. Scientists are confident in the presence of a rocky seafloor at the bottom of Europa's ocean. Hydrothermal activity could provide chemical nutrients that could support life. The best evidence for the existence of an ocean on Europa was gathered by NASA's Galileo spacecraft, which orbited Jupiter from 1995 to 2003. Although Europa lacks its magnetic field, as the Galileo spacecraft made 12 flybys of Europa, its magnetometer detected an internal magnetic field within Europa, as Jupiter's strong magnetic field swept past the Moon. Scientists believe that the most likely cause of this magnetic signature is a global salty water ocean. The bright, icy surface of Europa is unlike anything seen on Earth. It is the smoothest object in the solar system, with few towering mountains or deep chasms. Crisscrossing grooves and ridges break up the landscape. Many of these features resemble long, sinuous, dark-colored and slightly reddish streaks, some stretching across the surface in arcs over 600 miles, 1,000 kilometers long. Elsewhere, domes, pits, and chaotic ice blocks suggest that warm ice may well up from deep below. Europa's surface bears signs of a possible ocean beneath it. Images of Europa's surface reveal cracks and lineations indicative of a global ocean conducive to large tides deforming the surface. The two largest impact structures on Europa show concentric patterns, indicating that impacts may have penetrated Europa's ice shell into liquid water. Additionally, Europa's surface geology indicates warm ice has welled up through the ice shell, possibly from near the ice-ocean boundary. Models also suggest that Europa's icy shell is stretched and released by the gravitational pull of Jupiter as Europa orbits the giant planet. This squeezing and stretching is known as tidal flexing, and it generates heat within Europa. Tidal flexing has the potential to generate enough heat within Europa to sustain a liquid ocean beneath the surface. The ocean of Europa likely also directly contacts warm rock at the seafloor. As Europa orbits the gas giant planet, the icy interior of the moon is flexed. This flexing transmits energy into the moon's interior, which is then released as heat. Think about flexing a paperclip repeatedly and how it generates heat. The more the interior of the moon flexes, the more heat is generated. Interaction with warm rock could supply hydrothermal vents and other chemicals to the ocean. While input energy for life on Earth primarily comes from the sun, Europa's input energy could come from surface chemistry and interactions between water and rock on the seafloor. Moreover, if Europa's rocky seafloor is heated by tidal flexing, this process could provide energy in the form of chemical nutrients available in hydrothermal vent fluids. We know this type of process is possible because we see something similar at hydrothermal vents on Earth. Hydrothermal vents on Earth were first discovered in 1977 at the Galapagos Rift, a deep area in the Pacific Ocean, far from the coast of South America. Since then, many such vent systems have been found beneath the ocean floor of Earth. This discovery revolutionized our understanding of life on Earth and is considered one of the most significant discoveries ever made in ocean science. Saturn's moons. Similar to Jupiter, Saturn also has many satellites orbiting around it. The moons of Saturn came into focus in 2019 when researchers unveiled a topographic map of Titan, the largest moon of Saturn. This geological map was published in the journal Nature Astronomy based on radar data, infrared data, and other data collected by NASA's Cassini spacecraft. This spacecraft has been studying Saturn and its moons since 2004. Titan is located about 1.4 billion kilometers from the Sun, with a surface temperature of about 179 degrees Celsius, and surface pressure on this moon is more than 50% higher than that on Earth. Achieving such results involved a painstaking and costly process, driven by the desire to explore the universe for the betterment of human life. In other words, humans have hoped to find for themselves a new land as Earth becomes increasingly unstable, according to planetary geologist Rosalie Lopez of NASA's Jet Propulsion Laboratory. With a diameter of 5,150 kilometers, Titan is the second largest moon in the solar system, after Ganymede of Jupiter, and larger than Mercury. Titan is also the only known moon to have a dense atmosphere and is the only object, besides Earth, with clear evidence of stable surface liquids. Notably, organic compounds, carbon-based substances, crucial for the development of living organisms, play a leading role on Titan. The importance of organic compounds for life on Titan suggests the presence of liquid water oceans beneath its icy crust. organic compounds could permeate into the liquid water ocean and provide necessary nutrients for life if they exist on Titan. Research also indicates that flat plains, occupying about 65% of Titan's surface area, dunes and ridges, occupying 17%, create extensive frozen methane or other hydrocarbon patches at moderate elevations and equatorial regions. The Midland and Highland regions, believed to be the hard portions of the ice, cover 14% of Titan's surface. For a long time, Saturn has been the focus of many space studies, as its satellites suggest the possibility of life. At least to date, 20 moons have been found around Saturn, making its planetary ring system have more moons than any other celestial body in the solar system, noted by the International Astronomical Union. This discovery indicates that Saturn now has a total of 82 moons, while Jupiter ranks second with 79 moons. The moons of Saturn are relatively uniform in size, with diameters averaging about 5 kilometers. However, 17 of the 20 newly discovered moons have retrograde orbits, meaning they orbit Saturn and other moons in the opposite direction. This recent discovery belongs to astronomer Scott Shepard and the research team at the Carnegie Institution for Science using the Subaru telescope in Hawaii to locate the new moons. In 2018, Shepard and his team discovered 12 moons around Jupiter, including one with a retrograde orbit. So far, space exploration efforts, specifically the mission to search for life on Titan, have yielded promising results. Scientists have considered Titan the only moon resembling Earth, with lakes, rivers, and seas on its surface. However, at that time, it was believed that these lakes, rivers, and seas contained hydrocarbons, such as methane and ethane, rather than water. But now, with new research findings, there may be water on Titan. Not only Titan, but another interesting case within the family of Saturn's moons is Enceladus. In 2005, NASA's Cassini spacecraft orbiting Saturn discovered water jets erupting from cracks in the tiger stripes near the southern pole of Enceladus, propelling material into space and forming the E-ring of Saturn, the outermost large ring of the planet. This material was believed to originate from an underground ocean of liquid water hidden beneath the moon's icy crust. For a long time, scientists had suspected the existence of a subsurface ocean on Enceladus. They speculated that radioactive elements could provide enough heat to warm the moon's core, causing the surrounding ice layer to melt. Alternatively, the gravitational pull of Saturn may have heated Enceladus's core through a phenomenon similar to tidal forces on Earth. Both processes could occur simultaneously, creating an ocean as we see today. In many flybys near Enceladus, spanning 313 miles, 504 km, Cassini also detected other compounds. For example, dihydrogen, H2, and a variety of organic compounds containing carbon, including methane, CH4. Particularly, dihydrogen and methane are intriguing to astrobiologists. Scientists suggest that H2 could be generated by the interaction of rock and hot water on the seafloor of Enceladus, indicating the moon has hydrothermal vents deep beneath the ocean floor, a scenario akin to potential cradles of life on Earth. Moreover, H2 provides energy for some microorganisms on Earth to produce methane from carbon dioxide, in a process called methanogenesis. Similarly, something akin to this could be happening on Enceladus, especially since Cassini also detected carbon dioxide emissions and naturally occurring methane in the moon's plumes. Researchers wonder, could Earth-like microorganisms consume dihydrogen and produce methane, potentially explaining the large amount of methane Cassini detected? Therefore, Régis Ferrier, associate professor at the School of Ecology and Evolutionary Biology at the University of Arizona, and his colleagues have developed a series of mathematical models to assess the biological plausibility of Enceladus's methane production. This reveals a highly diverse spectrum. The research team examined whether observed H2 production could sustain a bacterial population on Enceladus and how this would affect the rates of H2 and methane escape in the plume. among other things. In essence, they not only could evaluate whether Cassini's observations are compatible with an environment conducive to life, but could also make quantitative predictions about the expected observations if methanogenesis indeed occurs at the bottom of Enceladus's ocean. Such evaluations will encourage those of us who hope that something is bubbling in the depths of Enceladus, optimizing for temperature. The research team concluded that purely abiotic hydrothermal chemistry, without the involvement of life, as we know it on Earth, cannot explain the methane concentration observed by Cassini. However, supplementing the contribution of methanogenic bacteria would uniquely fill this gap. To clarify, the recent study published last month in the journal Nature Astronomy does not establish the presence of life on Enceladus. For instance, it may be observed that the icy moon undergoes some kind of non-biological methane-producing reactions uncommon on Earth, possibly the decomposition of residual material since its formation, researchers suggest. Indeed, this hypothesis would be quite fitting if Enceladus formed from material rich in precursors, as some scientists believe. Parts of it will summarize the level of plausibility, and we believe that various hypotheses will begin to emerge. For example, if we assume that life on Enceladus is extremely unlikely, then such alternative non-biological mechanisms are more likely to occur, even if they are very different from what we know here on Earth. The next step will be to investigate whether hydrothermal vents exist at the bottom of Enceladus's ocean. The results of this search will help solidify Enceladus's status as a potential planet in the search for signs of life in space. The findings of these searches will bring about a new, exciting, and stimulating perspective. As shared by Linda Spiker, a scientist involved in the Cassini spacecraft project at NASA's Jet Propulsion Laboratory, studying water-bearing planets like Enceladus in the solar system provides a solid foundation for exploring the ocean worlds, planetary systems with water beyond Earth.